Good morning and welcome you all for today's lecture. So today we are going to discuss flat plate solar collector performance, how we determine performance analysis of the flat plate solar collector. Simply, we define how to find out thermal efficiency of flat plate solar collector and direct beam radiation and effective solar intensity reaching to the observer plate. All these parameters will be discussed so that things will become very easier to understand, because in our previous lecture we have discussed about heat removal factor of the flat plate solar collector, but before that topic needs a previous knowledge about flat plate solar collector thermal efficiency. That's why I think it is better to discuss about construction detail of the flat plate solar collector, cover plate, absorber plate, and tubes, which allows a fluid flow from these tubes, and how this fluid that will take away energy that is absorbed by the absorber plate, that will transfer to the fluid flowing through the tubes and taken out, and how you find out efficiency, thermal efficiency of flat solar collector. We are not going to discuss about exergy efficiency. First, we will use first law of thermodynamics, just law of energy balance to determine. So first, we will draw some basic schematic construction detail of the flat plate solar collector, and then define how to find out useful heat gain and incoming solar intensity on cover plate, and how much reaching to the observer plate. Then find out heat losses also, and then thermal efficiency. That is a part of discussion, so that basic idea about flat plate solar collector will become very clear. And this is a important topic from the examination point of view, particularly in Indian engineering services examination. Some most probably one question is asked about 20 marks from this topic. That's why I feel it is necessary to discuss here. So let us draw first collector details, and because we have to refer collector details and describing thermal performance of the collector. So first we draw it. So this is a detail of the collector. This you can see observer plate tubes. So it is a rectangular block collector. Simply flat plate solar collector is a rectangular block, and the tubes are arranged like this. So I will show separately how tubes are arranged here. So see, this is a collector tube. This is known as a collector tube. M mass is coming here. M. M is a rate of mass of fluid coming from outside, and this collector tube arrangement, this is a header. They are header. Diameter of header is higher than diameter of the tube. So fluid is coming. This arrangement is below the observer plate. Function of observer plate is to absorb radiation coming from the sun. Radiations are coming like this and reaching up to the observer plate. Sun radiation. After crossing the cover plate, that is a glazing. Topmost is a glazing, that is known as a cover plate made of the toughened glass. So this radiation is reaching here and absorbed by the observer plate, and there is a insulation, bottom insulation and side insulation, to prevent heat trapped by the observer plate to get lost in surrounding by conduction, convection, and radiation. The purpose of insulation is to trap the heat incoming from the crossing observer cover plate, that is made of the toughened glass, and then reaching to the observer plate made of the copper, blackened copper, and this tube arrangement is below the observer plate, sometimes above the observer plate, sometimes below the observer plate, and it is connected with the observer plate by using adhesive, metallic adhesive, conductive adhesive, or by use of the welding. The collector tube is properly attached with the observer plate by adhesive or welding, so that conduction heat will transfer from the observer plate to the collector tubes by conduction only. That is the only mode of heat transfer takes place inside the collector from observer plate to the tubes by conduction if collector tubes are not properly joined with the observer plate, then conduction of heat will not take place, so efficiency will go down. Only heat will be trapped by the collector tube by directly coming from the radiation. So that is very very less because area of the collector observer plate is much larger compared to area of the tube. So there is a one condition that these tubes should be properly attached with the observer plate for higher efficiency, higher thermal efficiency. So here and some losses will be also occurring, and when radiation go out from the surrounding, that will be collector losses because total heat energy will not be absorbed by the observer by the tube. So some radiation, in spite of having proper insulation, some radiation, some heat lost will take place due to temperature difference between surrounding and observer plate. So that analysis we are going to discuss here. To take a small figure, IT is a solar radiance coming on the cover plate. Total reaching on cover plate. AC area of cover plate. Cover plate is nothing but it is also known as a glazing and made of toughened glass, and around 3 to 5 range, thickness of the cover plate is 3 to 5 millimeter. Toughened, made of toughened glass having some ferric oxide particles so that it make a toughened. It has particular characteristics and it has very high transmissivity and low reflectivity. Transmissivity is very high, around 80 to 90%, and reflectivity is very low, 10 to 15%. That is a quality of the toughened glass, and that is requirement of the for the collector. ACG area and IT can be defined total radiation reaching, I total radiation reaching to the cover plate equal to IBN direct radiation, normal radiation into RB plus ID into RD plus IB plus ID into RR. Here we take IB means let us remove here N. Beam radiation. IB stands for the beam radiation. This is equation for total radiation reaching on the cover plate. Means total radiation reaching on the cover plate. How much radiation reaching up to this cover plate? That is a top plate. So IB means beam radiation, direct beam radiation, and RB is a tilt. RB is a tilt factor. Tilt factor for beam radiation, that is equal to cos theta upon cos theta z. Theta is the angle of inclination of the sunbeam radiation from the normal to the collector surface. Theta is the angle between incident radiation to the normal of the collector surface. Theta and theta z is a angle between sun radiation beam reaching to the collector and between normal to the plane surface. Normal to the plane surface. I will later define what is theta z and theta. So this is a tilt factor for the direct beam radiation, and RD. ID is a diffuse radiation because not only beam radiation reaches to the collector surface, collector cover plate, but also diffuse radiation. Radiation due to scattering from the dust particle, atmospheric molecules, and cloud. It reaches to the collector by diffusing X. So it is RD, and for it is ID, diffuse radiation intensity, multiplied by RD. That is a tilt factor for the diffuse radiation. Tilt factor for diffuse radiation equal to 1 plus cos beta by 2. Here beta is the angle of inclination of the collector surface from the horizontal. Beta is the angle of the tilt angle of the collector surface, collector face from the horizontal surface. That is known as a beta inclination angle. And here IB plus ID, and total radiation also reaching here due to refraction. Also due to refraction. So RR is a IB beam radiation, ID diffusion, and it will reaches to the cover plate by refraction also. Refraction from that one. And for refraction, tilt factor for refraction beam, refracted beam is RR. RR is a tilt factor. Tilt factor from the refracted beam. That is equal to rho 1 minus cos theta by 2. Here rho stands for the reflectivity. Reflectivity of the reflectivity of the cover plate means cover plate glazing, reflectivity of the glazing, the rho that is very less compared to transmissivity. This is a total radiation reaching on the cover plate. Total radiation reaching on the cover plate, IT. So how we can define, and what is the radiation reaching to the observer plate? How much radiation reaching to the observer plate? So that is defined as S. Collector, how much radiation intensity reaching to the, if it total radiation reaching to this surface, cover plate, and out of this, it is not total radiation that will reach to the observer plate. It will depend upon the transmissivity and absorptivity of the solar collector, cover plate and observer plate system. So it depends upon transmissivity and absorptivity, how much total radiation that is reaching to the cover plate will be absorbed by the observer plate. That is a S. S is a radiation intensity absorbed by the observer plate. So depend upon the product of the transmissivity of the cover plate and absorptivity of the observer plate. So that will depend upon the, so IB. Let us use another color here. S can be defined as S equal to IB RB tau alpha B. Means this is a beam radiation that is out of this, that is this part will reach to the observer plate, that will be absorbed by the observer, plus ID RD and plus IB plus ID RR multiplied by tau alpha D. This is a solar intensity absorbed by the observer plate. Out of this and product here, IBRB multiplied by tau alpha for the beam radiation. Tau alpha for the beam radiation, because this is a beam radiation. And out of this much will be reaching to the observer plate absorbed by, and this, and how much will be absorbed by the diffuse radiation. So ID plus RD plus total IB plus IDRR and multiplied by tau alpha diffuse radiation. Whether it is a part of the diffuse radiation or reflected radiation, it will be multiplied by tau alpha for the diffuse radiation. There is no any specific value of tau alpha for the reflected radiation. So that's why whole of this part will be multiplied by tau alpha d, that is diffuse radiation. So this much of energy is reaching to the observer plate will be absorbed by the observer plate. This is useful because this is energy that is useful for the conversion of heat energy from solar to the fluid that is flowing through the tube. So let us find out how much useful energy you can get. Useful heat gain by the collector. Useful heat gain by the collector. There are two ways, theoretical ways and practical ways, because you know that how much, you know here temperature Ti initial temperature, yeah, T inlet, and here T outlet. You will get T outlet. Here T outlet temperature. Here T outlet temperature, T out. You know T in and T out. T in and T out, and mass flow rate and Cp is a specific heat of the fluid. So you can get here useful heat gain Qu by equation mCp of the transport fluid, yeah, carrying fluid, energy carrying fluid Cp, and To out minus T in. That is useful heat gain. Another way you can find out by theoretical means. This is a practical means, because you know inlet temperature and outlet temperature, you know mass flow rate, and you already know what is a specific heat. If water is a working fluid, you know specific heat of water around 4.2 kilojoule per kg Kelvin. So any fluid if there is flowing through the tubes, we can find out Cp of that fluid and T out and T in by using by temperature sensors. We can find out T in and T out, what is the mass flow rate. We can also by using rotameter we can get mass flow rate. So this is very easy practically to find out useful heat gain. But how we can find out? This is also equal to S into area of the collector AP into S AP into S minus Q loss AP into S minus QL. AP means area of the observer plate. AP area of the observer plate, and S is a intensity of the solar radiation absorbed by the observer that already we have calculated. And here is a loss. This loss is comprised of the conduction loss, convection loss, and radiation loss. So simply we can write QL. And this equation we can also write like this: AP into S minus UL, overall loss coefficient, TP minus TA. Theoretically, we can also define Q useful by this equation. Q useful by this equation. So this is a here AP into S. That is a energy absorbed by the, but some energy will be also lost to the surrounding. So UL is a overall loss coefficient. UL equal to U top losses plus U bottom losses plus U side losses. Overall heat loss coefficient comprise of the top losses from the top, side losses like bottom losses by conduction or convection, and side losses by conduction. So these are losses comprising UL, overall loss coefficient equal to top losses to radiation, bottom losses conduction and convection, side losses convection and conduction. So this is UL, and TP is a observer plate temperature. TP is a observer plate temperature. T plate temperature, observer plate temperature. TA is a surrounding temperature. TA is a surrounding temperature, and AP is a area of the observer plate, which is a 10 to 15% lesser than area of the cover plate. Cover plate is on the top and observer plate on the inside the collector. So that is why AC is greater than AP. AC is greater than AP, around 10 to 15% greater than AP, observer plate. So this is a useful heat gain. You can represent by either this equation. This is a practical way of finding out useful heat gain, or by theoretical way you can use this equation of finding out useful heat gain rate per second. How much useful heat gain rate that is transferred to the flowing fluid to the tubes. That is a useful heat gain. Useful heat gain means useful heat gain by the observer plate, because still we are not talking about how much energy from observer plate reaching to the collector tubes. So this is a useful heat gain by the observer plate, and how much this will be transferred to the flowing fluid, that is a matter of discussion. That will comprise of collector efficiency factor, collector heat removal factor. Collector heat removal factor already we have defined in our previous lecture. So let us find out what is a thermal efficiency. Thermal efficiency of collector. Thermal efficiency of collector. N thermal equal to Q useful heat gain upon total radiation IT into AC. Because already we have calculated what is total radiation useful heat gained by the collector and how much energy is coming on the collector. That is a total radiation, total irradiance, total solar intensity reaching on the collector plate, collector cover, and ACJ area of the incoming radiation quantity, that is IT into S. And this is equation that you can use for the finding out thermal efficiency of the collector's plate-based solar collector. And this equation is also used for the finding out stagnation temperature, because whenever we collector design what is stagnation temperature means when there is a flow stop. Suppose flow is stopped and radiation is continuously coming. So what will be maximum temperature of the collector observer plate? And that is a very important, because if material inside temperature will go very high and material inside that are insulation, whether this insulation will be able to bear that temperature, whether collector observer plate can maybe melt, what kind of material we have to use in insulation and observer plate so that it will bear the high heating due to stoppage of flow of the working fluid. So that is a very important factor to decide collector stagnation temperature. In that case, you know that already we have calculated QU equal to APS minus UL TP minus TA. This equation is used for the finding out theoretical usefulity gain. In case of no fluid is flowing, when mass flow rate is zero, no fluid is entering, the useful heat gain becomes zero, useful heat gain becomes zero. So AP into S minus UL, and that case now TP will continuously rise and reaching up to maximum. That is maximum temperature is known as a T stagnation temperature. T stagnation temperature minus T ambient temperature in case of no fluid is flowing. So now solving this equation, AP S equal to UL T stagnation minus T ambient. So T stagnation means maximum temperature will be reaching equal to S upon UL plus TA. So yes, upon it, so you can see how T stagnation temperature is on what parameter T stagnation depends. So T stagnation means maximum temperature that reaching maximum temperature that observer plate will achieve. That is known as T stagnation equal to S upon UL plus TA. So that depend upon what is intensity, observer intensity, how much energy is absorbed. So you see here from this equation, higher the value of S means solar intensity reaching to the observer plate. If high, then then S stagnation will be high, and lesser the U value of overall loss coefficient. If overall loss coefficient is less, T stagnation will be more, and T ambient is constant during particular time. It's not depending upon, because this value is a constant. You can increase the solar intensity by designing collector in such a way that maximum intensity will reach to the observer plate. By increasing transmissivity of the collector, we can increase the S. If more heat is transferred from the cover plate to the observer plate, that will be higher S. And if side loss, overall loss coefficient, by increasing by using very high quality of the insulation material, by proper design of the collector, in this way we can reduce overall loss. These are parameters which prevent lesser the value of T stagnation. Lesser the value of T stagnation, more stability of the flat plate solar collector, because at higher temperature insulation will become unstable. That's why it should be minimum. This stagnation temperature should be minimum for proper. So I think this is enough for the understanding of the flat plate solar collector. And in next topic, we will discuss about transmissivity of the cover plate. Transmissivity of the cover plate depend upon the transmissivity and absorptivity, means reflection and refraction and absorption by the cover plate. Thank you very much for the watching this video, and please like and subscribe and share to your colleagues. Thank you very much.